course schedule 2. We have solved course schedule before. So the difference with course schedule 1 is that we need to return the ordering of courses we should take. So this is a topological sorting. So let's there are some prerequisites given, number of courses. Now let's jump into implementation right away. So now we need to return an integer array. So let's define our result and new int, and this will be size of known courses. And let's define our, so the way we're going to implement this, we'll have our adjacency list, and we will also count our in degrees. So and then from there, so we will be just like popping the in degree, decrementing it, and doing a BFS on it basically. And throughout the way, when we are popping our vertex which doesn't have any in degree, we will be adding it into our array. So this is just a topological sort cans algorithm. So integer list of integer. So this is our graph, which is hash map, and our integer in degree. Now let's go over our num courses. And what we are going to do is that we will saving for a given I. Initially we will just define the 0 in degrees, and also let's do the same thing for our result. Define them. So if there are no prerequisites, then we will just need to return our result, because these are just independent by itself and no need to even be in order, so it could be any order. So now let's go over our prerequisites. We can just prerequisites. Now let's define our parent. So our parent, so it is saying in this relationship we must take course B first if we want to take course A. So A is dependent on B. We can say B is our parent and child. So B is our parent, so this is 1. Now let's build our graph. Compute diff absent our child. So for val, if it's absent, then we'll just do a new empty array list. And let's do for our parent. And this is a directed graph, so let's add our child. And since we added our child, we can actually count our, increment our in degree values for this given child. Okay, now what we can do is we can check if this graph is empty or not. So if this is empty, that means there were no prerequisites, so we can return our result right away. Now let's do BFS in this graph. So we'll define our queue. Okay, now this queue will contain only vertices which has 0 in degree values. So let's traverse over our in degree map. Degree entry set. So we'll say if entry get value equals to 0, then include in our queue. Okay, now let's traverse it. So while queue is not empty, let's remove from our queue, and then that's our vertex. Okay, now since we have our vertex, we can actually assign it to our array. Result count this given vertex. Let's increment our value. And also now let's go over our edges, some other vertices and its children. So let's access it from our graph, and we'll try to get the vertex. If this vertex doesn't exist, then just empty array paste. So from here we can actually decrease, since we removed from our queue for this vertex, we can actually decrement our the in degree values for given vertex. So v so in degree get v decremented. So we are, I mean, this one is removed already. Now we are, because like this had 0 in degree values. Now we are decrementing it for given v and adding it to our queue. So if, however, only if in degree value equals to 0, then we add it to our queue. So given queue sounds good. So another thing to check if our count is not equals to given num courses, because like this means it was impossible to finish all courses, so there is some type of cycle going on in our graph. So we'll return empty array, and in the end our result will be returned. So time complexity in here, we can see that for each vertex we are going over of all those edges. So this is OV plus, overall time complexity is OV plus E, where V is all those vertices and E is all those edges. And I mean, we have all other loops going on in here, but overall time complexity is that one because that's what we are doing it. And for our extra space, we are utilizing extra space, and we can also say that it is O plus OV plus E, where V is vertices, E is all those edges, because for each vertex we are creating all those edges. Let's run our code. Let's submit. Nice.